Okay, introduction to engineering fans. Here we go. I am, of course, your genial host, Harry Whiting. All right, so in this course, we have gone through many of the design stages. The next one that we're going to discuss, or I'm going to discuss, and then you're going to send me emails eventually, is step number 5, the design defense. All right. So, why do engineers have to communicate? We're going to have to be able to communicate to supervisors, existing customers. We're going to have to put together periodic, detailed reports and negotiate with potential clients and with federal, municipal, county, state authorities. So, what we want is we want you to have idiomatic, polished speaking skills and grammatically correct English in written materials. That's one of the reasons that we have computer skills class. So engineers can spend any amount of time, up to 100% of their time, chasing contracts. I know my former boss, that was pretty much the description of his job. And I know that when I was consulting, that I would spend 4 or 5 times as much time looking for work as I did actually working for people. All right, so communications can be written, they can be email, spoken with someone, but we're going to have to communicate. So, when we're thinking about an oral defense of a project, what we're talking about is getting up and making a presentation about the project that you are proposing to do for someone. Now, there are a lot of circumstances under which you're going to be expected to get up and talk in front of people. That's one of the reasons why in an ordinary semester, we would have you get up and give the presentation of your project. Because we want you to get used to doing that now when the stakes are relatively low, so that when you get out, you have a job, you're a junior engineer or you're advancing through the ranks, that you'll be able to get up in front of people and talk. So, so we want to communicate that we've used the systematic approach in putting together the proposal that we have before people. We want to communicate how does our concept work, right? We've got to be able to explain that. We can't pass it off with a bunch of vague, well, there's input, there's output, and in between the miracle happens. No. What is the level of risk that we have with the project that we're talking about? Right? If it's, there are some projects there will be almost no risk. But there are projects where there will be a considerable amount of risk, and the people should understand that. And do the students appear to be teaming effectively? Well, that doesn't really affect your ordinary, the ordinary defense that you would do. All right, so you'll notice here they give us an outline. It's table 22.1. No, that can't possibly be right. Damn it, I thought I wouldn't need my book. Give me 1 second. All right, I have my book, my little pom-pom bookmark. And I cracked the book open. It can't be 22.1 because, as you saw at the beginning, we are in chapter 25. All right, so instead it's table 25.1. All right, so the organization of your presentation, for the title, they're saying 1 slide. The outline of the presentation, 1 slide. Problem definition, 1 slide. The important design requirements, 1 slide. Alternative concepts that weren't selected, they're saying 2 slides. Now, none of this is set in concrete, right? And you should feel free to be flexible about the number of slides. Oh, damn it. All right, final concept. Describe your main features, explain why you selected it. They're saying 1 to 2 slides. So if it's a simple enough project, you might be able to do it in 1 slide. If it's a super huge, complicated project, you may have to go beyond that 2 slides that they're suggesting. For the detailed design, show the main drawings, explain how the design works, explain how you make it or construct it. They're saying 2 slides. Again, these are only guidelines. Zero in on special features with close-up views, 1 to 2 slides. Present results of analyses, experiments, and models, 1 to 2 slides. Then the summary, we summarize the strengths of the design, quantify performance expectations, describe the strategy at the final competition. Okay, well, not necessarily competition. But they say that's on 1 slide. Now, these guys are particularly aiming your learning of design towards being able to compete in contests, design contests. This same organization works if you are a practicing engineer, so that you can put together a presentation about for a customer, for the county council, the city council, the state board, or even a national customer. All right, so table 25.2 tells us that we have strategies to reduce risk or ramp up, amplify the risk. Reducing the risk, we can use high quality concept drawings and detailed drawings. Okay, fantastic. We can use calculations, experiments, and models that establish proof of concept, explanation of manufacturing details, and quality visual aids. So in other words, the better our presentation looks, the more complete it is, the less risk there is. Now, there are things that amplify that risk. Poorly detailed drawings, one or more functions obviously will not work. No thought given to manufacturing. Always go over your presentation again and again and again. And rehearse your presentation, not sitting at your desk talking to yourself. Stand up and say it out loud, right? That helps get you into a state where you'll have more energy. All right. Table 25.3 gives oral presentation tips. So, tip number 1, do not read the sentences directly off the slides. I cannot tell you how many students I've had that give their whole presentation with their back to the audience because they don't know what's in their own presentation. So that brings us to our next one, which is look at the audience. You want to make contact with the people in the audience. I grew up in a theater family, as some of you may know, and my mother always used to say that as an actor, you want to be a little wood stove that is warming up the whole audience. Stand next to the screen when you're speaking and stand on the left-hand side of the screen, right? Now, not your left, the audience's left. Because in America, we read from left to right, so their tendency will be to come back to look at you as they're looking at the screen. Practice your presentation. My father used to say, the only way to be spontaneous is to rehearse. And be positive and dynamic. Nobody is going to be interested in what you say if you're standing there and you can barely be heard and you're just very low energy. No, come on. Be high energy. Walk around. But you need to be careful of one thing, and that is don't move too much. So you may or may not have noticed that my movements are always in sync with what I'm saying. And I stop the instant I've stopped talking. Blech. Now I may not talk right, but I do stop walking when I stop talking. So moving around and then I'm still. All right, tips on visual aids. First of all, avoid using too many words. Some of you have had my computer skills class, and you know I emphasize that. There is nothing stupider than a slide that is up on your PowerPoint that has 500 words. No. A few words, and then you talk and flesh out those few words on the screen. That goes with our next one, which is use a font size that can be seen easily. Right? You want a large font size. You don't want wee little tiny baby letters on there. Big fonts. Right? If you have too many words for one slide, make it 2 slides. Put in your concept or your detailed drawings and show what is your concept. A picture is worth 1,000 words. And if you have videos of testing your prototype, put that on there. If a picture is worth 1,000 words, what is a video worth? You want a title on every slide that says something about it. Show the results of calculations or experiments, right? You may need to, well, you probably have to interpret what that means for your audience, but that's why you're up there. You want to look like the all-knowing poobah who knows everything. View the projected images in advance so that you can make sure that all the words and pictures can be seen by the audience. Okay, in fact, I would go further than that. I would say view them from halfway back, however far away the audience is going to be, and get some friends in to look at your presentation so that they can tell you, okay, well, I thought this worked really well, but I really didn't understand what this picture was doing in this slide or whatever. All right. We are going to skip this slide. We are going to skip this slide as well. All right, man, we're moving along now. In a design competition, that's going to be somewhat different from a presentation to a customer or a government entity, but not a lot. So the quality of your drawings, again, makes a big difference. Evidence that you use calculations, experiments, and models will make people feel reassured. And visual representations of your results are more effective than saying you did them. Yes, again, a picture worth 1,000 words. Make sure it's a good picture. All right, so in summary, I can't believe how fast this chapter went. Engineers have to be able to speak and write effectively. Thorough planning and organization is your key to success in an oral defense of your design. Visuals are effective as 1,000 words, so good drawings, good pictures are essential. Okay, are there any questions? Well, silly question. I'm the only one in this room at the moment. All right, so what I'm going to do now is I am going to go ahead and close this. Let me remind you, you can email me at any time with your questions. Now, from chapter 25, I'm going to go to 27. I advise you to read 25, 26, 27, 28, 29, and 30. But they're very short chapters. Oh my God. Look through those because there will be questions about design on your final exam. All right, so we pick up with chapter 27. Why 27 and not 26? Well, in 26, they start talking about manufacturing and how that is done. But I just really don't think that's a very effective PowerPoint. If you read the chapter, you're going to be doing a lot better. All right, so let's plunge boldly into chapter 27, which is performance evaluation. All right, so what are metrics? Metrics are anything we can measure. So it might be force, momentum, speed, time that is appropriate to what your design is expected to do. Okay? But remember, measure the right things. Bad metrics lead to bad decisions. All right, so they are talking about the final competition. And we're not even going to worry about that. Grading, oh my God, get out of my face here with the grading. Now this is a way that we could measure how good a project that you have done, but I'm not going to go through that. And I'm not going to go through that either. So we're already done almost. Metrics are physical criteria that distinguish your project from those of the other people. Now, competition is always skewed towards those who have finished the previous design milestones in good order. All right, let me say some more about performance evaluation. Anytime we design, we are going to do experiments and maybe even make prototypes along the way that we can test the performance envelope, right? And sometimes we're going to find out our performance is so much better than what was required, but very often we're going to find out, well, it performs but not as well as we want. We have to go back to the drawing board and think about it some more. Some things we're not going to be able to do prototypes of. When we first design an airplane, we're not going to be able to make a prototype unless it's a very small airplane, right? If we're talking a huge 4-engine airliner, we're not going to be able to build a prototype before we get approval from the people who are financing the whole thing. If we're going to build a nuclear power plant, we're not going to be able to build a prototype at all. When if the design is approved, we're just going to start building that plant. That would be the same pretty much with any building, that when we design a building, we are going to build that building after the plans are approved. Anything we can do to measure the performance before we start building or while we're designing is going to be a good thing. And that is something that we really want to do. Oh, right. All right, so that was chapter 27. All right, here we have chapter 28. Chapter 28 is the design report. And where is the, there you go, slideshow button. All right, so the design report is something that we're going to have to put together, whether it's a project here at school or whether it is a project you're doing as a professional engineer. There will have to be a project report or a design report. If you do a project, you'll have to do a report too. All right, so we're going to talk about three different things within this. One is illustrations. How do we make good pictures? Next is instructions. And the third is the reports. All right, so our illustrations, right? You can see here that we have figure 1 in this mass of text, right? We want to cross-reference that all over the place. So you don't just stick a picture or an illustration in there and hope that they look at it or read it. No, you make a reference to it. Figure 1 shows the ... whatever. Right? So we want to make sure that we are referring to the illustrations we're putting in our report. We want always a figure or a table title. You don't just leave it in there and hope that they can interpret what it is. In fact, assume they won't know what it is. We want our cross-references to be near the reference. Sometimes this is hard because our illustration is actually very large and it won't fit on the same page with where we need to reference. Use plenty of labels as they're required. Go wild with labels at first and then figure out which ones you can eliminate because they're not needed. Okay, so we see these illustrations and they help clue the audience in as to what we're talking about. In this case, they're talking about the air pressure valve. And I don't know if you can see it, but this lower left-hand illustration, kind of fuzzy, not the best. But sometimes that's the best picture you can get with the equipment you have. God knows I've had that problem before. Then they show where does that fit in to part of the bicycle, and then where does that fit in the larger scheme of things. Right? So you'll notice though, it's from the bicycle, they've got a circled portion and an arrow that comes down to where you see, you see a larger illustration of it, and then it with an arrow that comes down and shows this is the air pressure valve. All right, illustrations should be understandable. In other words, we don't want an illustration that is enigmatic, if I may so describe it. Right? We want an illustration that shows us something that we would not understand otherwise, and make sure we make sure that we understand that well. All right, so I am looking at this, and we have the tube coming down. We see how this part goes together, and it's an exploded drawing where we see all the parts that go together there all at once. All right, so you'll notice they did Scatterplot. In other words, where are the performance parameters, right? You'll notice that it's velocity on the y-axis and time on the x-axis. They have the curve of the theoretical performance, and then they have the circles show where their points of actual performance were. Right? So when we make something like that, we want to label both axes. We want to include the units that we're talking about. We are going to put in a legend that says what is what. We use a continuous line for our theoretical, but we use discrete points for the measurements that we made when we were doing our testing. Colors don't always come out well. In fact, I noticed there is a curve on this PowerPoint that I see here on my on the computer screen, but did not even come out on the PowerPoint. Don't get fancy with your colors. Be very careful about using colors, and be very straightforward. Use black and white most of the time. Only use colors when you have big, bold things like a histogram that you're going to show. And you might want to make sure that you're using lines that have different symbology. You see, this line is a dotted line, and this one is solid. Okay, so we want to represent data as effectively as we can. All right, so this table 1 is about 3 different printers, a Morton, an IQ, and an Overture. Boy, I don't even know if those are real printers or not. All right, so one thing they put down is the height in inches. Okay, so we've got that comparison. We've got the width in inches as well, back and forth. The depth in inches, right? So that gives you the cubic volume that a printer would occupy, and the weight in pounds. You'll notice all of these say what is the type of unit that we're using. Okay, so when we put in an equation, we do it as part of a sentence. The total harmonic distortion, THD, of voltage is defined in equation 1 as THDK equals the square root quantity of the summation from H equals 2 to capital H of the absolute value of voltage K given H squared divided by the absolute value of voltage K at 1. Okay? We always number our equations for easy reference, so that if we're going through the report and we say, and if you remember from equation 5, right, we want them to be able to say, well, wait, I'm not sure I do remember equation 5. We want them to be able to back up and look at that and find it easily. We want to be sure that we are defining all the terms in our equation. Right? So gear tooth stress, which we're going to call S, is calculated by XS equals WT times PD divided by the quantity F times Y times K. Right? Where we say WT is the tangential force, PD is the pitch diameter, F is, oh, damn it, now we'll never know what F is. Well, I mean, if you really want to know, you can look up gear tooth stress in Google, and they'll probably give you some equations and tell you what that should be. All right, so when we put together a design report, we have an introduction, we have a body of the report, and we have an end. So in the beginning, we explain what is it, why is it important, what are the required supplies, and explain the format that you're using. Okay, so the introduction can be pretty short, but I remember the wise advice given to me by one of my graduate advisors, which was you always over-explain in a report, right? So even if you think it's a report that's only going to be read by academics, don't just put in a bunch of academic jargon. Make sure you're explaining it so an ordinary person could read this report. All right, so in the middle, you want to go step by step through the process of how you got there. You would start with your initial sketches or concept drawings, show how that evolved to the next step in drawings and how you used models or experiments to show what would work and what wouldn't, down through how you made your prototype or how you plan to make your prototype or project, all the way through to what would be the end of the project. Then in the end, we summarize everything we said before, right? This does not have to be a super long section, but make sure that you explain what the conclusion is of your project or your design, and what is the future prospects for it. We believe that this could revolutionize how people get drinking water on the Navajo Nation. Right? There you've got an idea right away, and your perspective could also be, if you're trying to sell a design to somebody who's going to make it or who's going to buy it, say, we expect to sell 10,000 units in the first year, something of that nature. All right, we put in appendices that supplement our report, right? In other words, we're trying to make sure that we are as clear as possible. So we will have an appendix that includes our raw data, that has all of the calculations we did. An appendix that has all our preliminary sketches and all the drawings for our alternative designs. You may have to put a written description in your appendix to make sure that you don't just have a bunch of stuff in there and say, there you go, there's the appendix. You want your report to reference each appendix, right? So you're going along and you say, our calculation was that this would be able to withstand 5,000 tons of force, and the calculations for that are in Appendix 1. Don't place unreferenced material in the appendix. And there you go. A design report of design reports. All right, so what I'm going to do is I'm going to make PDF copies of these and send them along. Again, read the chapters from 25 through 30. It's only a few pages in the book. Let me see exactly how many pages that is. Oh, hey, I've been looking for that. Where's my table of contents? All right, so chapter 25 starts on 469 and goes to, and chapter 30 ends on 512. All right, so that's 31, 40, that's about 42 pages of reading. I have confidence that as college students, you could read that. Okay, well, thank you very much. Again, send me your emails with questions. I will set up a Zoom meeting for class next week where everybody can log in, we can talk to each other, see where people are sitting. But until then, when the fields are white with daisies, we'll meet again.